Greetings to the conference participants. We present a report on the topic Microprocessor System for Calibrating the Antenna Position Sensor. Authors: Nadia Kryva, Nadia Gashchyn, Serii Glado, Halyna Semenyshyn, Nataliya Stadnyk. Introduction. When positioning satellite communication antenna systems in space, it is necessary to orient them along two coordinates azimuth and elevation. The most convenient way to do this is by using a position sensor installed on the movable part of the antenna, which needs to be spatially oriented. The sensor should consist of the following components: a magnetometer and an accelerometer mounted on a single platform, rigidly connected to the movable part of the antenna, as well as a satellite positioning signal receiver and a microprocessor board that processes their signals and controls the antenna's operation. The magnetometer determines the direction of the Earth's magnetic field and, accordingly, the magnetic azimuth. The accelerometer makes it possible to determine the spatial orientation of the antenna in the Earth's gravitational field, which defines its tilt relative to the Earth's surface elevation angle. The sensor consists of an accelerometer and magnetometer rigidly fixed to a non-magnetic platform and precisely aligned with each other so that their x, y, and z axes are aligned. In this case, when the platform mounted on the antenna is rotated, the coordinates of both devices and the projections of the gravitational force vector and the magnetic field will change synchronously according to the calculated dependencies, considering that the natural components of these vectors in the stationary reference frame on the Earth's surface remain constant at the chosen point. Let us examine the vector components in the coordinate system of the magnetometer and accelerometer, as shown in figures 1 and 2. By measuring the component values of vectors provided by the magnetometer and accelerometer, it is easy to determine the direction of the corresponding vector. This calibration process involves several steps to determine both the sensitivity coefficients for each coordinate and the corresponding offset of the 0 point for the gravity, acceleration and magnetic field vector sensors. The obtained calibration coefficients are stored in the microprocessor's non-volatile memory and are subsequently used for positioning and controlling the operation of the antenna system. The sensor platform is mounted onto a rotating device with axes aligned as shown in Figure 3. A slow rotation is performed with a set increment around the horizontal axis, which corresponds to the z-axis of both devices. The microcontroller periodically captures readings from both the accelerometer and magnetometer. In this configuration, the x and y components of the accelerometer vector change, while the z-axis reading remains low, primarily determined by the offset of the z-axis channel. Next, the platform is repositioned so that the horizontal rotation axis aligns with the y-axis of both devices. Figure 4. The same slow rotation and data recording process is repeated. In this orientation, the x and z values change similarly to the previous setup, and the y-axis signal remains low. The datasets obtained through this process represent real, synchronously recorded raw uncalibrated values from the accelerometer and magnetometer. The 0-point offset of each channel along its respective axis can be determined using known mathematical relationships. The calibration coefficients along the axes are determined based on the condition that the maximum calibrated value equals the acceleration due to gravity g. Thus, the actual values of the acceleration vector components along the corresponding axes of the accelerometer, taking calibration into account, are determined by the following formulas. The second step of the calibration process involves determining the coefficients for the magnetometer. During rotation, as shown in figures 3 and 4, the components of the magnetic field aligned with the axis of rotation remain constant, while the other two coordinates vary from minimum to maximum values. Similar to the accelerometer, the 0-point offsets for the magnetometer channels are represented as To determine the sensitivity coefficients for each channel of the magnetometer, we use the array of measured data, taking into account the compensation for zero-point offsets. In these instances, the magnitude of the magnetic field vector can be determined using only the two non-zero components. We obtain four equations to calculate the magnitude of the magnetic field vector. To determine the angular parameters of the magnetic field vector S direction, it is sufficient to know the ratios between its vector components, without taking into account the actual magnitude of the magnetic field vector. Therefore, we can arbitrarily assume that the coefficient mx equals 1. By equating the first two equations, we have obtained the calculated values of the magnetic field vector components, accurate up to a constant multiplier, can be expressed as follows. After calibration, the direction of the true gravitational acceleration vector g and the magnetic field vector m in the coordinate system associated with the platform can be determined using the direction cosine formulas, in the form. Accordingly, taking into account the properties of the scalar dot product of vectors, the angle delta between these vectors is determined by the formula, which can serve as an additional source for calibration verification during system operation and provides the ability to filter out random disturbances during measurements, particularly those typical for magnetic field sensors. Conclusions. The proposed calibration method for the antenna system's position sensor improves the pointing accuracy of the antenna system and reduces manufacturing costs by eliminating the need for precise angular position sensors on the azimuth elevation unit. Additionally, it removes the requirement for precise initial setup of the antenna, which is especially important for mobile and portable antenna systems. Thank you for your attention.